Welcome to 8.4, where the graphing is super crazy. You're definitely going to want a graphing calculator today so that you can get a good picture of what's going on, because it's tough to do without making a table with a lot of decimal points in it. So today our graphs are going to have x's on both top and bottom. The function, so there's some rules you got to learn here. First of all, the function has a vertical asymptote anywhere where the bottom can equal 0. We saw that yesterday. The difference is that today you might have more than one vertical asymptote. The function might have a horizontal asymptote, or it might not. If the degree, so degree means the exponents on top or the degree means the exponents of the polynomial. If the degree on the top, a means top, is bigger than the bottom, then there is no horizontal. So maybe I'm gonna try and write that here. Top. That's gonna be here too. Bottom. Okay. So if the top has bigger exponents than the bottom, then there is no horizontal asymptotes. If the top has smaller exponents than the bottom, then there is a horizontal asymptote at the y equals 0, or just right there on the axis. If the degree of the top and the bottom are the same, then the asymptote is at the line y equals leading coefficient of A divided by leading coefficient of B. I know it was a lot of weird, confusing information. Let's check it out. So when I look at this kind of first picture here, there is no horizontal asymptote because, again, the degree is 2. The degree on this one, since it's not written, would be just 1. And if the top is bigger than the bottom, then there is no horizontal asymptote. Okay, here, there is no, the degree is, there's no, where it's got a 2 here. The top is smaller than the bottom. That means there is one horizontal asymptote at the axis. Over here, they both just have an exponent of 1. So that means there is a horizontal asymptote at leading coefficient divided by leading coefficient. That would be 2 divided by 1, which is just 2. Which, if I look here, I notice this is scaled by 2's. Otherwise, how the heck did they get to 4 here, right? It is at 2 on that line there. Okay? So, calculators at the ready. What we're going to do, I say graph, you say table, but of course today we're going to be a little nicer about it and instead plug this into our calculator. So, my biggest suggestion to you is to make sure that you use parentheses to close in the entire top and the entire bottom. So when I look at mine, it says parentheses, x squared minus x minus 6, parentheses, divided by, parentheses, x plus 1, parentheses. And when I hit graph, I can see just kind of a rough sketch over here that it looks something like that. Okay, sorry for my arrows being kind of funky, but that's what it looks like. So to find the vertical asymptotes, I'm looking for where the bottom equals 0. So take the bottom, put it equal to 0. So the vertical asymptote is at x equals -1, which, well, if you look at my graphing calculator, that's what it looks like. Not so much on my little sketch over here, but I promise on my graphing calculator it does. Horizontal asymptote, well, hang on a second. Degree of 2, degree of 1. If the top is bigger than the bottom, then there is no horizontal asymptote. Okay, and then of course graphing it, I see that in my calculator. I want to define oblique asymptotes. An oblique asymptote is an asymptote that is not perfectly horizontal or perfectly vertical. I don't know that we're going to spend a lot of time looking at those. Let me think. Do we want to do this one? I don't think so. I want to go on to this one. Okay. Another example. We're going to graph this first this time, and see what we think. So when I graph this, and if you have a graphing calculator, that would be great if you're following along. Parentheses, x squared plus 4x minus 5. Make sure you close those parentheses before you hit that division sign. 4x plus 5. And when I hit graph, I'm fully expecting something super funky, and I am surprised because what I actually see looks like this. Some calculators will just leave a blank. Some of them might have put a circle, but this is what I see. And I'm really confused by that because everything else today is going to be super funky with all sorts of curves and wee and things like that, right? Like what just happened. Let's look more specifically at the function we were given. Maybe we try simplifying it like we did the other day. Back to the top, what adds to 4 but multiplies to negative 5? I think that's going to be a positive 5 and a negative 1. What do you guys think? That adds to 4 but multiplies to negative 5. Whoa, 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 whoa. X plus 5, that cancels, and all I'm left with is x minus 1. Hold up a second. That looks a lot like y equals mx plus b. In this case, my y-intercept being negative 1. And then it goes up 1 over 1, up 1 over 1, kind of, sort of. Pretend my graph is perfect. If you look at the actual graphing calculator, it looks fantastically, exactly, like a y equals mx plus b line. That's why it graphs to be a straight line. However, the function is not a linear function. Even though it graphs to be a straight line, it's not a linear function. And this is important because, look at this x plus 5. It's on the bottom. So you still need to say that there is like an asymptote right there. So what I'm going to do is I'm going to take that bottom, set it equal to 0, and I know that x cannot equal 5. Now, an asymptote really likes to be called an asymptote if you have a graph approaching the line but never crossing it, which is not what that looks like on the graph that I have up here. So here we just call these a point of discontinuity. You can also just call it a hole in the graph. And if you were looking at this on an actual calculator, you'll notice that that is at negative 5. I forgot my negative sign down there. Right there. And that's how, if you had to show it on paper, you would just draw like a little circle there. Also, here's one where you can see where they have just drawn a circle there because there's a hole in that graph. Okay, that is it for today.